My name is Frank Petty, and this is my final presentation on coin calorimetry. So first we need to talk about specific heat capacity. Specific heat capacity is a property of all materials. It's the amount of heat energy required to raise the temperature of a unit mass of some sort of material by 1 degree Celsius. And it represents how well a material can store and transfer heat energy, because heat and temperature are not the same thing. So a material with a high specific heat capacity will be able to transfer a lot more heat from the same amount of temperature as a material with a low specific heat capacity. So calorimetry is a way we can measure the specific heat capacity of a certain substance by measuring the change of temperature in a system where another material is present that we know the specific heat capacity of. So commonly water is used, which has a specific heat capacity of 4.184, and it's a good material because it allows easy heat conductivity, and we know the specific heat capacity. So here's a diagram of a calorimeter. We have the water, and then you have adiabatic walls that keep the system in thermal isolation, so we could have minimal thermal energy being lost to the environment. And the object will will give its thermal energy, transfer thermal energy to the water, and we can measure the change of temperature in the water, and then we can use that to calculate the change in the heat of the water. And from the conservation of energy, the amount of energy that the water gained will be the same as the amount of heat energy that the object lost. And we can use the formula Q equals mc delta T to find the specific heat capacity then of the material that we're trying to measure, where Q is heat, M is mass, C is specific heat capacity, and delta T is the change in temperature. So in my project, I calculated the specific heat capacity of 4 US coins: pennies, nickels, dimes, and quarters. And you can see I've set up the equations for the conservation of heat energy here, which is basically taking the equation we had earlier, Q equals mc delta T. And since the two Q's are equal, we can set the mc delta T components of both materials equal. So we have mass of the water times the specific heat capacity of the water times the change in temperature of the water equals the same thing for the coins. And then we can easily solve this equation for the specific heat capacity of the coins in terms of the other variables. And we find that it is dependent upon the mass of the water, specific heat capacity of the water, the change in temperature of the water, and then the mass of the coins and the change in temperature of the coins. So now that we understand the theory behind this experiment, we can look at the materials. So I needed multiple of each coin, a scale to weigh the coins, a hot plate to heat up the coins, tongs or scoop to remove the hot coins, a beaker to heat the coins in, a styrofoam cup I used as my calorimeter, a temperature probe, and a computer with the LabPro software to run the temperature probe. So here's my procedure. I'm also submitting the slides to this, and my procedure is also listed in my final project report. So I won't go in too much detail here, but basically I recorded the mass of the coins, and then I heated the coins on the hot plate, and then I put the hot coins in the calorimeter and measured the change in temperature of the water. And then once I had calculated all the variables I needed, I plugged them into the equation and solved for the specific heat capacity of the coins. And then I also took it a step further and looked up what the coins were made of and found some values for the specific heat capacity of those alloys that the coins are made of, so that I could compare my results. So here is a table of my results from when I used the calorimeter. So I've recorded the mass of the coins, the mass of the water. I used 100 milliliters of water, which is 100 grams of water in each case. The way I heated the coins was by putting them in boiling water that was close to 100 degrees Celsius. And I boiled the coins for 5 minutes. So then by that point, I assumed that the coins had come into thermal equilibrium with the water. So instead of measuring the temperature of the coins directly, which would be impossible to do, I measured the temperature of the water, and I could assume that I could use that for the temperature of the coins. Then I measured the initial water temperature in the styrofoam cup in the calorimeter. And then I measured the final system temperature, and the final system temperature can be used for the change in the coin temperature and the change in the water temperature, because I assume that at the final system temperature, those two have come into equilibrium, so they're equal. So the final coin temperature equals the final water temperature. I've also recorded the number of coins, but a key thing to note here is the number of coins doesn't matter. This isn't necessary for my experiment. You just need the mass of the coins, but I have recorded the coins for replication purposes of my experiment. So if someone thought that I didn't use enough coins, I didn't have enough material, they could use more in the future. So going back to our equations, I have some values, but I still haven't exactly calculated the change in temperature of the water or the change in temperature of the coins. So I'm going to do that real quick in this table. And once I have all the values that I need, I can simply plug it into the equation I wrote earlier to find the specific heat capacities of the coins. And I found that they were all around 0.44 joules per gram degree Celsius. And then some sources of error in my project. Some of the when I took the coins out of the hot bath, they were a bit wet. They had hot water on them. So this hot water would have added more heat to the system than just the coins. So this is a systematic error, and it would result in an overestimation of the specific heat capacity of the coins. Also, when I transferred the coins from the boiling beaker to the calorimeter, they lost just a minimal amount of heat energy to the air during that small transfer time. And this would result in this would be a systematic underestimation of the specific heat capacity. Also, as I mentioned before, there's no way for us to measure the temperature of the coins directly. The temperature probe can't do that. So I had to assume perfect thermal equilibrium. So all of my coin temperatures are reliant on that thermal equilibrium, which in theory, perfect thermal equilibrium can't ever be reached unless you have an infinite amount of time. So that is sort of I think a random error in my experiment. So conclusions, the coins, as we saw before, have a relatively identical specific heat capacities. And this makes sense because they're all made of an alloy of copper and nickel called cupronickel. And since they're all made of the same material, that same material would have the same specific heat capacity. Now there are some slight variations in the exact alloys in the coins, which I think resulted in a little bit of variation in the specific heat capacities I measured. And then I went online and I found that an accepted value for the specific heat capacity of cupronickel, which the coins are made of, is 0.377 joules per gram degree Celsius. And this is pretty close to my values, so I feel pretty confident in my experiment. Here are the references I used to find the makeups of the coins and the specific heat capacities of those alloys that made up the coins. Thank you for listening to my presentation. My email is listed here in case there are any questions.